may face too much of difficulties in terms of environment, in terms of society. Many problems we may definitely face. Whatever the current technology, if we continue, if we use for the longer term. So for that one, only the solution is the sustainability. So we need to be design the products in a sustainable manner. So then only it can be possible to achieve the net zero emission point of view, and also it can be possible to follow the sustainable development goals. That is the first priority. So those things I will discuss in terms of the sustainability. Next thing is the nanotechnology. So already it is evolutionary. So in many fields, nanotechnology play a key role in terms of the technology point, development point of view, in terms of the portability point of view. In all the cases, nanotechnology in terms of the efficiency point of view play a crucial role. So we need to understand nanotechnology. First, we need to understand what is the importance of the sustainability. Next, we need to understand how nanotechnology will help to develop the sustainable designs or sustainable based products. So those things we can understand. Then coming to the point of white LEDs. So for the electronic devices, particularly from the lighting point of view, how white LEDs play a key role. So if we utilize the two terminology like sustainability and also nanotechnology, if we combine these two for the development of the white LEDs, how it can be useful for the future generation devices and future generation applications. So maybe in the introduction you may hear about my research areas and all those things. Mostly I am working in the nanotechnology and the sustainability point of view. So long back only I am working in terms of the white LEDs point of view, but whatever the works previously I done at the PhD time, so those things I will try to discuss. So moreover this FDP closely related to the research point of view. So whatever the works we have done in terms of the white LEDs point of view, I will project here. So maybe after tea break, the real research what I am doing related to the hydrogen fuel point of view. So particularly in terms of the sustainable hydrogen point of view, what are the energy devices it can be possible to develop within the laboratory. So those devices, how it can be helpful for the sustainable development goals, all those things also I will discuss. So I think this is the introduction already over. So now coming to the point of the first thing, sustainability point. So why do we need to think about the sustainability? So compared to our forefathers and present, also if you think of compared to our forefathers and present, so a lot of new technologies already developed. Still we are thinking, still we are doing a lot of research. So to develop the new products, to improve the efficiency of the products. So but particularly we are thinking in terms of the sustainability point of view. If we think in that direction only, it can be possible to develop the new products which can be useful for the future generation. So the very recent survey done by the Rice University students, so USA, what they have noticed that maybe in the 2050, the majority crisis is the energy. So we may get the water, we may get the sufficient of the food. Maybe in the near future, we may face the problem in terms of the energy. So not only the no need to wait up to the 2050. So in 2026 also we may face a lot of problems in terms of the energy point of view. If somewhere two countries they war in between the two countries all over the world, they are affecting in terms of the energy point of view. So definitely we need to think towards the energy point of view. So definitely we need to develop the new energy devices, new energy technologies which can be useful and without creating the emissions like CO2 emissions. So without affecting to the environment, so those kind of the devices we need to be developed. So if we develop those kind of the technology, automatically we can easily follow these sustainable development goals. So if you think about the environment, if you think about the economy, at the same time if you think about the society point of view, automatically most of the sustainable development goals, it comes under the tree of the sustainable development. If you follow these three pillars of the sustainable development, so it can be possible to almost all the sustainable development goals. It can be possible to work towards in this direction. So, particularly my research area in terms of the energy point of view, so particularly we are working in terms of the sustainable development goals 5, 6, 7, 11, 12, 13 and 17, particularly in terms of the energy point of view. So water also another problem. So maybe in the, after the energy, so if you see in the previous slide, as per the survey, energy as well as the water also major problem in the 2020. So purification of the water technologies. And that case also materials and material based semiconductor materials, those things are very important. Those materials also we need to be developed in terms of the sustainability manner. Then only it can be useful for the real life applications. Like whatever the food waste we have, from that one we can create the carbon material. From that carbon materials we can prepare the supercapacitors or battery materials. And also whatever the agriculture waste we have, from that one also it can be possible to generate. And so much of e-waste is there. From that one how we can recycle that one. Those materials how it can be useful for the energy applications. And also multidisciplinary point of view. Only one material we need to be developed. Those material it can be useful for the multiple applications. Suppose I am preparing one kind of the semiconductor material. It can be useful for the lighting application. It can be useful for the energy application. Same material it can be useful for the water purification or some other application. So like that kind of the materials we need to be developed. That material also eco-friendly manner. So if we develop these kind of the technologies, if we implement this kind of the methodology for the preparation of the materials, it can be possible to overcome the present energy demand and also lot of in terms of the water point of view, all these problems it can be possible to overcome. So for all these things, only the thing is we need to be do the effective research, and then from that one we need to identify innovative materials. Those materials it can be useful for the multiple applications. So now coming to the our FDP point of view, particularly in terms of the white LEDs. That means in terms of the electricity point of view. So suppose as like the previously mostly we are using the tungsten based lamps and all those things. So now almost we are replacing those kind of the lamps with the upcoming generation of the white LEDs. So why this much of importance? Why we need to be focused in this white LEDs? What is the advantages of this kind of the white LEDs? So if you see here, white LEDs point of view, it have the very long life. So a typical white LED lamp can last even for the 1000 hours if we develop the effective white LEDs. So the thing is, here we know that what is the importance of the white LEDs and also what is the history of the white LEDs also. Then only the thing is how we can prepare these kind of LEDs. So I hope most of you guys are aware about that what is the lightning principle and how LEDs, LED principle and all those things. So those basics I don't want to go in detail. So now we will think how this kind of the white LEDs, what are the ways it can be possible to create this kind of the white LEDs at the research laboratory level. So what are the materials still lacking, which kind of the materials we need to be focused for the preparation of the white light LEDs. Those things we will try to understand here. So moreover, particularly white LEDs, why don't we use the other LEDs? So the best thing is it have the low power consumption. So if you use this kind of the white LEDs, it can be possible to energy saving point of view and also environmental friendliness. So emission of the CO2 level is very less, and also cool operating temperatures and high brightening and efficiency, long durability. So durability is one of the best thing in the case of the white LEDs. And also fast response, lack of toxic mercury. So this is one of the, in terms of, if you think about the sustainability point of view, whatever the materials we are going to be used, that should be eco-friendly, that should be environmental friendly. So in that point of view, instead of using the mercury materials for the lighting applications, we can use the eco-friendly materials for the development of the lightweight fabrications point of view. So now, considering the next generation lighting source, particularly, so we need to be focused on the methods of the white lights. So I hope many of you are aware about that, what is the methods available in terms of the white light diodes. So particularly, so most of the cases in general, if you read the textbooks, so mixing of the RGB, so then we can easily get the white. So another way is the UV light. So on that one, RGB phosphorus materials, if you put, then it can be possible to create the white light LEDs. And also in method one, blue LED we use. So different kinds of the phosphorus materials like lithium, aluminum, graphite, this kind of material, or RG phosphorus, these kind of the materials if we use, it can be possible to generate the white LEDs. So now white light it can be possible to generate. So now what is the role? So particularly in terms of the phosphorus type of materials. So whether it can be possible to generate these kind of the phosphorus materials with the low cost materials, and also simply doping with some other materials, rare earth materials, whether it can be possible to generate the white light. So those are the main research topics in the white light LEDs. So now we will see in this topic, particularly I will focus on the phosphorus materials. So as you know, phosphorus it is a luminescent substrate that emits light when excited by the radiation. So it will be used for the multiple applications like display devices, lighting devices. Many applications are there. Mostly they are using also in the real life applications also. So now the thing is how effectively we can prepare the phosphorus materials to generate the white light. That is the main thing we need to be focused. So we need to be develop this kind of the white light generating luminescent materials with the low cost materials. That is the main target in the research area. So now let's see. In the first method, there are many disadvantages also there. So poor color rendering index, narrow visible range, high color temperature, lack of red complement. That is the main difficulty. There are two methods we discussed right previously. In that one, method one have the some of the disadvantages. In method two, advantages is the high CRI, high color temperature, high conversion efficiency into the visible range. So now we need to be focused on the host materials. So there are many kind of the host materials available which can be possible to generate the white light. So now among the four different types of the host materials, particularly phosphates and borates, compared to the other like vanadium, molybdenate, silicate, tungstenate, there are many phosphates are there. Particularly in this one, phosphates and borates are the one of the best advantages we have to create the white light. So why only phosphates and borates? Why not vanadates and molybdenates? You can understand once we enter into the research point of view. So in addition to that one, main advantages of these phosphates and borates, it have the large band gap, high chemical stability, high stability, and visible luminescence, low sintering temperatures. Low sintering temperature is one of the best advantages for the preparation of these materials. So even below 1000 nits, it is one of the best sintering temperatures, particularly these kind of the phosphorus materials creations point of view. So most of the research laboratories, more than 1200, 1300 like that we are normally using. So minimal temperature, minimum 1000 to 800 nit by to remove the impurities when we are preparing this kind of the phosphate materials or borate kind of the materials which can be useful for the lighting applications. And also in terms of when we are selecting the host materials, either in the case of the phosphate materials or borate materials, so which can be particularly in terms of the alkaline earth materials. So if you choose those kind of the elements in terms of the price point of view, it is very less price compared to the other transition metals or some other materials point of view. That means selection of the host material, that means alkaline materials and also doping materials from the rare earth elements also very key role for the generation of the white light. That one we need to be understand. So particularly in the kind of alkaline elements point of view, so if you choose sodium or potassium kind of the materials, it's low cost. So we can easily prepare this kind of the materials. And alkaline earth materials point of view, calcium and barium, this kind of the materials if you choose, we can easily prepare this kind of the materials. And also anyway, rare earth elements depends on our applications point of view, either samarium, EU or MD. So those things we can choose based on our applications point of view. Suppose if you need only blue light emission, so only red emission. So if you whatever the rare earth element you are choosing, based on that one, it can be possible to generate the white light. So now, particularly my research point of view, I am choosing the sodium or potassium, calcium, these kind of the materials, and also in terms of the rare earth elements point of view, basic doping materials like samarium and U kind of the materials I am choosing. So now, why I am choosing these materials also ionic radius point of view. So normally the doping, whatever the doping elements we are choosing, like the rare earth elements, the ionic radius should be lesser compared to the host kind of. Then only it can be possible to doping point. Once the rare earth elements sit on the host material, it can be possible to generate the emission point. So these things also, whenever we are choosing the alkaline material or the rare earth element, so these properties, ionic radius property is one of the important property before choosing any kind of the elements. Suppose if you choose a higher radius of the dopant material, we cannot properly dope to the host. It can be maybe some kind of the alloy kind of thing. Suppose host in the one place, another dopant maybe in the surface or somewhere, it cannot be possible to go inside to the host material. So if it is the alloy or cluster kind of the formation, if you see, it cannot exhibit the proper luminescence properties. So those things we need to be taken care before choosing the any kind of the either host materials or the dopant materials. And another thing is, so now we know that the importance of the white light LEDs, and also we know that which kind of the materials it can be exhibited for the better synthesis point of view, either alkaline materials or rare earth element material. Now, in what stage we can prepare this kind of material? Whether we can prepare the bulk materials or we can make the materials up to the nano scale. So if we prepare the bulk material, if we prepare the nano materials, I think most of you guys are aware about that. So bulk materials, physical and electrical properties completely different compared to the nano materials. So many best examples if you take AU materials, so even in terms of the color point of view, if you change the size from 1 nanometer to the 10 nanometer, even the gold color also it will be changed. And also lightning point of view also. So if you change the zinc selenide material size from 1 nanometer to the 10 nanometer, it can be possible to tune the lightning properties from blue to complete red also based on the size of the crystal. So that means preparation of the materials, whatever the materials you choose, preparation of the materials in terms of the nano, it plays a crucial role, and also efficiency or some other properties also it may play a crucial role for the lightning applications point of view. That's why now we need to understand how these nanomaterials nanotechnology will effectively we need to use for the development of the lightning applications point of view, particularly in terms of the materials preparation point of view. So we all are already aware about that. What does it mean by the nanotechnology? What are the revolutions happen in terms of with respect to the nanotechnology point of view, and also what is the history of the nanotechnology? Also, everything we already know that. Then how we can implement this nanotechnology effectively for the different applications is the important factor. So we know these technologies. So where we can use this kind of the nanotechnology in an effective manner, that is only the play a key role for the future generation devices point of view. So I don't think so we need to go in detail about the nanotechnology and all those things, because in the BTech first year itself one chapter is there. So most of even students also they get aware about these things. So nanotechnology is the important thing. So now let's see, there are different applications also there. So here from the 1980 onwards, so there are a rapid development in terms of the nanotechnology point of view, particularly in Indian research laboratories also. Almost all over the India, many research labs they are working in terms of the nanomaterials preparation and then different applications point of view. And also it's not a big difficulty for the preparation of this kind of the nanomaterials or analysis point of view also. Simply even in our chemistry laboratory also, we can easily prepare these kind of the nanomaterials for the different applications also. So particularly in India point of view, so when they established the research center at the Bangalore, JNSCR, from that onwards, CNR Rao, I hope everyone heard his name, India's premier scientist. With his knowledge only in India, the terminology in terms of the nano point of view, he made significant contributions. So he made even good research laboratories at JNSCR. So with his revolutionary ideas, so he built in terms of the nanotechnology point of view, he made significant contributions. So even this one, so most of the things in terms of the nano point of view, what we need to understand, so whether with these materials we can prepare in which dimensions we need to be reduced. Whether we need to prepare the one-dimensional nanostructures or zero-dimensional nanostructures, or in terms of the thin film, whatever the requirement we have, so we need to build this kind of the nanomaterials by tuning the experimental techniques. So particularly in terms of the nanoparticles point of view, nanowires point of view, thin films point of view, so in general way, most of the people what we may think, so whether if you prepare any kind of the nanomaterial, it is within the 100 nanometer size, maybe it is the nano. So, but as a physics point of view, as a chemistry point of view, if you see the term, motion of electron are constrained in any one of the dimensions. So then only we can think or we can talk about this kind of the nanomaterials. That means when you are talking about the quantum confinement effect, so this terminology, deep with wavelength play a key role. So all these are the very fundamental things in terms of the nanomaterials. Once you go through, you can easily understand. So my main focus is so which kind of the materials we need to be prepared. Either it is the zero-dimensional, one-dimensional or two-dimensional materials. What is the importance of these dimensions? So particularly in terms of the energy devices, recombination is the one of the major difficulties. So suppose if you prepare the zero-dimensional nanostructures, so the particles are aligned nearby to the one of the another particle. So suppose when the light illuminates, it can be excited, it can be easily transferred to the other particles. So the lifetime of the electron is very less in the case of the nanoparticles point of view. Same material, same application, same light illumination. If you do in terms of the nanowires or nanotubes point of view, the electrical conductivity is much higher. because that once the electron excited in the case of the nanowires or nanotubes, it can be transported for more longer time compared to the nanoparticles. Now, this is one of the simple example what I am giving here. That means the dimensionality of the nanomaterials play a key role in terms of the physical properties, in terms of the chemical properties, and also electrical properties. Particularly in terms of the electrical properties point of view, these kind of the one-dimensional nanostructures play a key role compared to the zero-dimensional nanostructures. So, depends on the applications point of view. Of course, zero-dimensional also, some of the medical applications, it is very key role because of the very small size. We need to inject very small amount of the nano point of view in terms of the nanoparticles point of view. At that time, nanoparticles play a key role. So some cases nanowires or nanotubes it will play a key role. In terms of the photo detectors point of view, in terms of the defense applications point of view, thin film technologies are very, very important. So maybe even in terms of the self-cleaning kind of the windows, maybe you may hear about this one. Simply using the TA nanostructures when you prepare the thin films, and if you use this kind of the windows using those kind of the materials, automatically it will be clean with respect to the sunlight. So self-cleaning kind of the material. So only the material, we already studied about this one, PaO2 materials, how to prepare, how to do these things. Only we are implementing those kind of the simple applications point of view. And moreover, whatever the materials we are using here, many cosmetic and other applications also, simply this kind of the nanomaterials they are using. That means whatever we are studying in the textbook, those applications, if you think this kind of the materials can be useful for the different applications, if you implement those kind of the technologies for the real applications, there are plenty of chance to gain the financial point of view also. So mostly the cosmetics point of view, I give one of the example. So we all know that the sunlight it have the consisting of different types of the wavelength. So UV light, if you fall onto our bodies, it may create some problem. So the only the cosmetics whatever we are using, that will protect from the UV light. So those kind of the thing, what is the simple application? So we need to be, which can be absorb the UV light, those kind of the semiconductor we can generate and use it for the cosmetic applications. Then automatically these materials, nanomaterials will be useful. So UV light protecting means mostly zinc sulfide materials or PaO2 materials. If you see the cosmetics materials point of view, mostly these kind of the nanomaterials will be used. So finally, what I am trying to say is nanomaterials have plenty of applications. So we need to be effectively prepare these kind of nanomaterials, and we need to use it for the different applications point of view. So even in terms of the sensors point of view, photo detectors point of view, so lot of applications are there. Even in terms of the sensing, lighting, displaying materials point of view, most of the flexible photo detectors nowadays even bend are flexible kind of the photo detectors using the nanomaterials only they are preparing. In terms of the nanomedicines point of view, artificial muscles. So in many cases, these nanomaterials playing a key role. So when I am teaching to the students, I am just showing this video. So like that way they understand what is the role of the nano. So whatever the future, in terms of the future devices, without nano it cannot be possible to design any kind of the materials also. So I hope now, what in terms of the FDP title point of view, now we can clearly understand that what is the importance of the sustainability and also what is the importance of the nanomaterials point of view. Now another thing is the white light LEDs. Those importance also we already discussed, importance of the white light LEDs. Now at the research point of view, how we can prepare. So particularly I focus on the phosphorus material. Those kind of the phosphorus materials or borate material, how we can prepare in terms of the nano point of view and the research laboratory point of view. So mostly we are using this kind of the dopant materials, and these materials we have chosen. So sodium and calcium E2O9 point of view, and iodium coating of the barium materials, and different types of the NaSr, BA4. All these materials also, even solid state reaction method also you can be possible to prepare. So even if you don't have the laboratory also, no need to be worried. So if you have this kind of the chemicals, simple mortar and pestle is good enough. With mobile furnace, you can prepare these kind of the those materials. So now, once you prepare this kind of the materials, another thing is the characterization of the materials. So once either this material it have the high purity or not, whether any other phases existing within the material or not, we need to be identified. So for that one, anyway, XRD, FTAR, this kind of the analysis is required. So anytime, whenever you want FTAR and DRS spectrum within my research laboratory we have. So once you prepare the sample and bring it to my research laboratory, you can get these kind of the DRS and FTR data with free cost. Okay, and maybe within 1 or 2 months we are going to be install the XRD and FTSEC also integrate the. So I think XRD 2 crores we are going to be invest, and 3 crores for the FTSEC. So soon, maybe within 2 months or 3 months, we are going to be install this XRD and FTSEC facilities also. That means once we prepare the materials, most of the characteristics future applications. So previous discussion also we already understand that major problem is the energy point of view. So in the upcoming years, maybe in 2050, we may face the main problem in terms of the energy point of view. For that point of view, particularly hydrogen fuel based emitters or fuel cell technologies, how we can design. So fuel cell which can be useful for the net zero emission. We use the hydrogen as the fuel as the energy source. The output is the H2. So those kind of the devices, how we can build, how we can develop. So for all these cases, the primary thing is the production of the hydrogen. Once we need to produce the hydrogen, so those hydrogen we need to store it in a proper way. That hydrogen we need to be connect for the fuel cell and then generate the electricity. Those things we will try to discuss. I hope for the maximum 1 hour or 1 hour. So here, particularly my research main focus also hydrogen fuel production. So these 3 topics we are working: water purification point of view, CO2 reduction, as well as the hydrogen fuel production. All the experimental facilities already be established. It is readily available at the CMI research laboratory. And my research lab name also catalytic materials for renewable energy. So in that lab, main focus is 3 applications. All the experimental facilities are available. Someone have really interest in these domains. So and also energy domains. This one, energy point of view, hydrogen fuel, even CO2 reduction. So the harmful CO2 reduction we will collect using the semiconductor material. We are converting into the useful fuels part. Those technologies also we are using. Water purification, industrial water we are collecting. From that one, we are using some of the techniques, and then we are making it purified water that is useful for the agricultural applications. So all these 3 areas we are doing. So for all these 3 areas, one of the important and major thing is the preparation of the material. So if you design novel materials, if you design a efficient materials, same material it can be useful for all three applications. So that's why first important thing is the materials, that is catalytic materials. Catalytic which can be promote the reaction process. So in all these three cases also mostly we are using the solar energy as the source. From the solar energy we are trying to split the water to produce the hydrogen. Same solar energy we are using for the CO2 reduction. Same solar energy we are using for the water purification also. In all these three cases solar energy is the important. So solar energy, if you want to observe, means whatever the materials we are developing, that should be harvest the complete spectrum of the solar energy. But unfortunately, most of the semiconductor materials what we have the lack of absorption capability, harvesting capability. Maybe some materials it can be harvested only UV light. Some of the semiconductor it can be harvested only visible light. Some of the materials only it can be harvested. Most of the semiconductor it can be available which can be harvested UV light. But unfortunately, the solar spectrum consisting of only 5% of the UV light, remaining 40 and 30% visible and NIR light. Available semiconductor it can be harvested UV light, but the solar spectrum only 5%. So for all these things, only the solution is we need to make the novel materials which can be nanocomposites or microstructured material, these kind of the materials. We make it combined and then complete solar spectrum we need to make. That means some of the UV material, visible light material, NIR material, all three together we can make it as a one compound, and then complete solar spectrum we need to be harvest and use it for the different applications like hydrogen, CO2 or water purification. That is the main motto in our lab what we are doing. Preparation of the catalytic materials which can be harvested the complete spectrum of the solar energy. That material can be useful for the real application of the hydrogen fuel, CO2 reduction and water purification technology. So for that reason, completely in terms of the materials point of view, mainly we are focusing the materials which can be prepared from the ortho-based material, carbonous materials, porous materials, and the single atom nanocatalyst. Maybe you may hear, I don't know about the single atom nanocatalyst. In the previous section, we discussed about the nanomaterials. Nanomaterials is combined of the different small atoms. So why we need to combine all these atoms and we can make it as a one single crystal? Why don't we use as a single atom itself as a catalyst? So why we need to waste this kind of all the materials? So for that one, nowadays how they are doing, even single atom can be act as a catalyst and useful for the applications. No need to waste the bulk kind of the material. Even single atom we need to be controlled with the surrounding of the carbon materials and then use this kind of the single atom catalyst for the different energy storage as well as the conversion applications. That is the research trend it is going on in terms of the single atom catalyst. And also in terms of the ortho based also I already discussed. So two results also I will show how we are converting this kind of the ortho materials for the real life applications. And the carbon materials, mainly we are focusing on the graphene materials, CV and core materials, some additional carbon based materials which can be useful for the energy conversion as well as the energy storage applications. And also porous materials like metal, organic, frameworks materials, so which can be highly useful for the CO2 conversion or CO2 absorption. So any material which have the high porosity, those materials may be highly useful for the energy. So for that reason, metal organic framework is one of the best options for the energy applications. But the difficulty is the high yield. Getting the high yield in terms of the metal organic frameworks is very difficult. So if we will overcome those difficulties, metal organic frameworks, hydrogen storage point of view, some other applications point of view, one of the best materials in terms of the energy research point of view. So anyway, I will try to discuss in terms of the different materials. So particularly in terms of the carbon-based materials in our research laboratory, we are focusing zero-dimensional like C60 carbon dots, graphene quantum dots also we are preparing using the micro program by using the simple technique, and also from the leaves, different plant leaves also it can be possible to generate the carbon graphene quantum dots also. So those kind of the ones also we are working. In terms of the carbon nanotubes using the chemical technique, we are creating the carbon nanotubes and functional groups we are changing and using for the energy and environmental applications point of view. Two-dimensional material point of view, graphene materials we are using. As many of you are aware about that, graphene is a two-dimensional structure. So what we did recently is why don't we convert the graphene two-dimensional to the three-dimensional structure? That into very lightweight kind of the materials. So for that reason, what we made is graphene. We look and then we made it as a three-dimensional aerogel, which can be constructed as a three-dimensional structure with a high porosity point. And also even one gram of graphene, if you convert to the aerogel, normally one gram of graphene if you take and convert to the aerogel, it will have a very less weight, and then it can be possible to float on the surface of the water. So water purification point of view, what we did is, so we made, if you mix the graphene materials to the water, it will contaminate and somewhat some of the graphene it will be dissolved in the water. Same graphene, if you convert it into the aerogel and make it as a less weight and then float on the surface of the water, it can be absorbed all the pollutant, it can be absorbed and then completely convert the pollutant water into the clean water. And then say that aerogel we can keep it aside, so without damaging to the real water. So that kind of things also we have developed in the graphene by converting the graphene aerogel. And in terms of the three-dimensional point of view, metal organic frameworks and high ordered mesopores, biochars also we made. And these mainly different electrode materials applications point of view, water applications point of view, we are using. And in terms of the agriculture-based derived carbon point of view, as you see, this kind of the materials we take cotton husk and coffee related grounds and using the endeavors, first we activate this one and using the high temperature and we convert it as a two-dimensional materials. As you see, no chemicals we are using except endeavor materials, and then we are creating the two-dimensional sheets kind of the materials and using for the solar applications. So, and also yield also very high. So using the waste materials study, we are creating the health kind of materials. So for energy storage and coffee nuts point of view, also similar kind of the materials we are creating. All the nanos materials we have created are two-dimensional materials. These materials we are using in terms of the energy storage, energy conversion, and also water purification applications. So different temperatures, if you vary, it can be possible to vary the surface area of this. So these kind of the application materials we have developed at the laboratory, and these all these kind of the works published in very good international publications. So in terms of the two-dimensional materials point of view, I already explained, even in the C3 and 4 kind of materials we have focused, and then using for the energy storage as well as the hydrogen production and the CO2 reduction applications point of view. From the graphene point of view, we make the graph from the graphite to graphene we integrate. From that one, reduce the graphene by eliminating the functional groups using the simple alpha notation. So we are changing the electrical conductivity from the graphene to the reducer graphene oxide. So with respect of the conductivity point of view, it can be effectively used for the photocatalytic or photoelectrocatalytic applications also. we developed different types of the composites also with the combination of the graphene and other materials. And ordered mesoporous materials also we have. So as you see, this kind of complete ordered structure. So if you design this kind of the nanomaterials, the electron will transfer from one end to the another end without deviation. So that means prolonging the lifetime of the electron, it can be possible these kind of the porous ordered nanostructure. And also because of this porous nature, it have the high surface area also. So with that surface area, more catalytic reactions will take place. So particularly we are using P123. So using this one and whatever the photoactive materials we are incorporated in this one, and then we use it for the multiple applications. And these are the simple mechanism how we grow the porous structure and all those things. So metal organic frameworks, very simple metal organic framework, AICTE, that means zinc based metal organic framework, cobalt based metal organic framework. We can easily prepare these metal organic frameworks, highly porous materials. So in our research laboratory, AICTE-67 we made, and iron based MIL, and many MIF ZF8 also we made, and we published nearly 15 to 20 journals with respect to the metal organic frameworks. So those who are really interested in terms of the metal organic framework, this kind of ZF67, ZF8 is the one of the best option to prepare these kind of the materials and use it for the different applications. So in the preparation of the metal MOF material, even we can use the solvothermal materials and the solvothermal technique, hydrothermal technique, even electrochemical deposition also it can be possible to grow this kind of the metal organic framework. Even simple sono-chemical technique also it can be possible to grow the metal organic frameworks. The synthesis method is very easy, but only the thing is the final yield, whatever the chemicals we are using as the precursor materials, the final product we are getting very less of. We need, if you overcome this difficulty, these are the one of the best materials for the application of the civil integration. Maybe you may hear about the last Nobel Prize, so related to the metal organic frameworks. So that kind of effective materials for the CO2 reduction or CO2 absorption for metal organic frameworks. And as I said, from the metal organic frameworks, it can be possible to prepare the single atom catalyst also, because metal organic framework itself it can be have a carbon nature. So those carbon layers it can be protect the metal atoms, and then it can be possible to make a single atom nanocatalyst. So one single atom surrounding it can be carbon material, another single atom. So we are separating the each atom and then make it active for the application of the energy storage as well as the energy conversion application. So in addition to that one, we are working on the perovskite based materials. So these perovskite materials, light absorbing property we have. The only problem what we have noticing in this kind of the perovskite materials is the stability point. So when we illuminate it with the light intensity, after some duration of the time, it is converted into the active materials to the inert material. So that is the disadvantage in the case of the perovskite materials. So nowadays solar cells, one of the best options. Perovskite to solar cells is one of the leading research case of the solar cells. But there also they are struggling in terms of the stability point of view when we use the perovskite material as the source of the solar cells. Even same phenomena we observed in terms of the energy storage as well as the energy conversion applications. So in addition to that one, photocatalytic point of view, metal semiconductor materials are very important. So because it can be harvest the solar energy and used for the conversion of the solar to conversion of the hydrogen and all those things. So in our research laboratory, as you see, using the simple chemical vapor deposition technique, we made this kind of the morphologies and nanowires, nanorods, nanobelts kind of thing also. So simply what we did is we changed the substrate temperature, carrier gas flow, we changed substrate position, we have changed, and the growth time we have varied, and we may see this kind of beautiful morphologies of the elements. So interconnected nanorods, interconnected nanobelts, these kind of the architectures also we have developed. So the only the thing is we have changed the substrate position. This is the source material, this is the substrate what we have here. So if you change this position also, the growth, once it is evaporated, the material it carry with the inert gas and then fall onto the substrate material. If you change these parameters like substrate temperature, carrier gas flow, it can be possible to prove this kind of different types of the morphologies also. So what we only the thing what we need is this kind of the setup with the tubular furnace with the gas flow conditions. So we can do any kind of the morphologies and use it for different applications. Even hydrothermal techniques also, we have what we have used, serious hydrothermal technique we use. So there we simply tune the solvents. So ethylene diamide with respect to the water we have used, simply changing the concentration of the solutions, we have noticed the different morphologies. As you see here in the last thing, from the microspheres to the narrow belts kind of materials also we have created using the simple hydrothermal. So particularly, so now I think you may got the clarity which kind of the materials we have. So which kind of the material it can be useful for the energy and metal operations point of view. Particularly in terms of the energy production point of view, so I will give the importance of particularly the solar energy. So as you know, nearly 1000 terawatts of the solar energy heat on the surface of the earth. So the current total energy consumption is only 30 terawatts. That means whatever the surface, whatever the solar energy heat on the surface of the earth, if we utilize only 1% of the solar energy, it is more than enough for the current energy. So plenty of solar energy is available, that is freely available. As a researchers, we are unable to use those kind of the solar energy for the practical applications right now. So at least 1% of the solar energy, we are unable to utilize it for the practical applications right now. Where we are lacking. So even though several kind of the semiconductor materials we have, light harvesting property we know that, photovoltaic effect even since 1970s itself we know that. We know the working principle, we know the semiconductor materials, still we are lacking to convert the solar energy for the real life applications. So that is only 1% of solar energy also we are unable to convert it as a part of practical applications. So when we think in this direction, the only the thing is the solar energy spectrum. So solar energy, as I already explained, in the solar energy maximum UV light is only the 5%, the visible light is the 44%, NIR is the 37%. But the available semiconductor materials, what we have, mostly it can be absorbed the UV light. So that is the main problem. So when you develop the new semiconductor materials, which can be harvest the visible light or NIR light, then it can be possible to conversion of the solar energy for the practical applications. That is the lack in the research area. So in this direction, everyone needs to be focused. We need to develop the new semiconductor materials which can be harvest the complete spectrum of the solar. Then it can be useful for the solar cell applications and different applications also. So many of you are aware about that what are the ways of the solar energy harvesting also. So main thing is the solar cells. I hope everyone knows how the solar cell working principle and also currently which kind of the solar materials we are using and which kind of the generation of the solar cells we are using. So mainly based on the generation point of view, three types of the solar cell: first generation, second generation, and third generation solar cells. Unfortunately, commercially, still we are using the first generation solar cells. That means silicon based solar cells only we are using for practical applications. Second generation solar cell, it is the thin film based solar cells. Third generation solar cells is the quantum dots based solar cells or perovskite solar cells. These all are under the category of the third generation. So no need. Most of the research labs they are working in the second generation and third generation solar cell. Still we are unable to make it as a commercial application. That's why still we are depending on the first generation solar cells, which can be developed in the 1970s based on the silicon materials. Still we are depending on that one and we are making it useful for the commercial application of solar cells. Maybe you may hear that you may have doubt. The silicon solar cells also silicon have the bandwidth of 1.1 L. How we can use it and how it can be possible converting the visible light or NIR light for the practical application of the city. So then if you think about the nanotechnology point of view, we may get the answer for this. So when we reduce the size from the bulk to the nanoscale, then it can be possible to tune the band gap. So with that property, the mechanism of the silicon solar cells also you can easily understand. In the second generation thin film based, so it can be possible to flexible kind of the semiconductor materials. So in the case of the thin film solar cells. So some of the countries they are already made as a commercialization flexible kind of the solar cells. So even for the windows, some other places also in the roof of the houses, all those cases also they are using. That means flexible kind of the solar cells. That is the second generation solar cells. Third generation, if we use the quantum dot materials or perovskite materials, that is related to the third generation solar cells. And the second way of the conversion of the solar energy is the solar to thermal energy. That means solar energy capture and then use it for in the form of the heat energy. So solar cookers, solar heaters, all these are under the category of the solar to the thermal point. In the third one, solar to the chemicals point. So in all these two cases, either solar to electricity point of view or solar to the thermal point of view, if you see, it can be occupied a lot of space to set the solar panels and the conversion of all these things. But in the case of the solar to the chemical point of view, you can harvest the solar energy and make it as a chemical and store it in a small device. Whenever you want those kind of the energy, you can use it. That means no need to occupy a lot of space. You can easily store the solar energy in the form of the chemical point of view and then make it useful whenever you need. So in that one of the hydrogen energy also one of the key for the solar to chemical energy point of view. That means you need to harness the solar energy and split the water and then produce the hydrogen. Those hydrogen can be stored in the form of the metal hydrates or some other storage devices, and then whenever you want to use it for the real life applications, you can use those kind of the storage devices and generate the electricity. That means solar energy in the form of the chemical point of view we are storing and then using for the practical applications. That is related to the solar to the chemical. So my research area mainly focus on the solar to the chemicals point of view, particularly in terms of the hydrogen point of view. So we need to generate the hydrogen and then we want to use it hydrogen for the different kinds of the applications. This hydrogen also, there are many ways to produce the hydrogen. So in that case also we need to be, just I will check. Very fundamental basics I didn't add in this PPT. So mostly research point of view I have added. So in terms of the hydrogen fuel production point of view also, there are different techniques available So in the techniques, particularly photoelectrochemical or photocatalysis technique is the one of the best techniques because it can be used the solar energy for the practical applications. So only simply we want to use the solar energy and make it as a conversion of the hydrogen and then use it for the fuel cell applications. So in all these cases also for the hydrogen fuel production point of view also, the thing is materials. So which kind of the materials we are using for the practical applications. That is the main important thing. So for our applications, we choose the cadmium sulfide based materials. So these materials, it can be harnessed for visible light. So most of the problem is the UV and NIR. So that's why I choose the cadmium sulfide based materials, and then these materials have the band gap in the range of the visible rays. So we can easily harvest the visible energy and make it as a hydrogen fuel from the semiconductor materials with the help of the solar energy. So in the laboratory, what we did is CDS material we prepared with the different dimensionality, 0-dimensional, 1-dimensional, and 2-dimensional nanomaterials, simply by changing the solutions using the hydrothermal technique. So here what we did is, if we use the only DI water as a solvent, we have noticed the spherical shape of the molecules. So when we add little bit of amount of the ethylene diamine to the solution, then we have noticed the nano rod-like molecule. So if we completely use the ethylene diamine, we have noticed the nano rod mixture. When we use a metal sheet kind of the compound. So now, single material, we make the different types of the dimensional of the materials. With these materials, we have verified the hydrogen evaluation. So when we verify this kind of the hydrogen, if you see in this graph, compared to the 0-dimensional or 2-dimensional nanostructures, 1-dimensional nanostructures exhibiting the extraordinarily hydrogen evaluation rate. Here, nearly 2.5 micromoles of within the 1 hour, this serious nanorods producing the hydrogen. So now we have doubt. So same material we are using, same light intensity we are irradiating. Then based on the morphology, it is getting the different hydrogen evaluation rate. So then we realize that what is the reason behind in this one? Why 0-dimensional exhibiting the less hydrogen? And why only 1-dimensional exhibiting the high hydrogen kind of thing. Then when we do the impedance analysis and band potentials, when we observe that one, we have noticed that 1-dimensional have the high electrical conductivity and also lifetime of the electron is very high in the case of the 1-dimensional nanostructures. So that is the reason for the production of the high amount of the hydrogen. And also when we notice the band potentials also, so 1-dimensional exhibiting the suitable band potentials for the hydrogen. That is one of the other advantages in the case of the 1-dimensional nanostructures. But in the case of the 1-dimensional nanostructures also, if you see, the hydrogen rate is very low because only one semiconductor materials we are using. Maybe this kind of the material is useful for the hydrogen fuel production, but it is not possible to make it as a commercial radiation because the amount of the hydrogen is very less. So for that one, what we did is simply we add the dopant materials like PD and PT kind of the materials. That means that materials also we use the liquid laser ablation. So simply using the LDR laser, we hit the metal and make a fine tune of the nanomaterials we prepare. If you see this kind of the materials, very fine spherical shape of the materials we have developed with the help of the LDR laser. So those materials already optimized series nanorods we incorporate on the surface like this PD metals. This is the CDS and remaining is the PD or PD nanoparticles we will incorporate on the surface of the CDS nanorods. At that time, if you see how much of high hydrogen we have produced, CDS itself only 2.5 micromole. When we add the PD or PD materials or PD composite materials, nearly 125 micromoles of the hydrogen we are achieving. So almost 10 to 20 times higher the hydrogen we have produced. Simply adding small amount of the metal on the surface of the CDS electrons. So now we realize that maybe these kind of the materials may be called, if you develop the device with this kind of the materials, it may be useful for the application of the production of the hydrogen. Simply solar energy heat on the surface of the semiconductor material and then producing the hydrogen. Even industrial scale also it can be possible with this kind of the material. But another problem what we have noticed here is whatever the materials we are using, either PD or PD materials, in terms of the commercialization point of view, it is highly expensive material. So because of the rare elements point of view, either PD or PD materials, it is the rarest metals. So we are unable to use it for the industrial applications point of view. So the next thought what we have is we need to replace this kind of the rare elements with the transition metals. So we want to find those kind of the materials, but same kind of the efficiency we want to achieve. So in this direction, we go for the MOS2 materials. MOS2 is the transition metal sulfides materials. We prepare the MOS2 bulk material and we have incorporated on the series material. At that time, we have noticed a very minute amount of the material. So MOS2 is suitable for the hydrogen production, but when we use the bulk material on the surface of the CDS materials, it was exhibiting very little amount of the hydrogen. So then we dig into the research, and what we did is using very simple ultrasonication technique. Instead of using the bulk MOS2, we made the few layers of the MOS2 material. Layered member we change using the ultrasonication technique. MOS2, we have the MO is the metal surface on the top and also bottom is the surface sulfur element. These sulfur elements contribute for the hydrogen. When you make it as a thin layer, more number of the sulfur atoms may actively participate for the hydrogen and then produce the high amount of the hydrogen. So, like that technique, we create using the ultrasonication technique, and then we make the different layered bulk to thin layer, alpha thin layer, from 52 layers of the MOS2 to 2 layers of the MOS2, different layers we made using the ultrasonication technique, and then we incorporated into the series. At the time you see nearly 124.49 millimoles of hydrogen we are generating. If you see in the previous slide, when you use the PD and PD materials also, almost similar kind of the hydrogen. That means it can be possible to replace the noble materials with the transition metal sulfides materials with the low price materials. So this is the research. I think maybe you may aware about the Journal of Material Chemistry here, one of the premier journal in the RSC publications. We have the impact factor of 30 impact factor. So one of the very high standard. So at the time we have published these results in the Journal of Material Chemistry. When this kind of work, when I worked at the postdoctoral at South Korea University, there we developed this kind of materials. So later, this kind of the doping concepts and the nano-composite concepts, several techniques we have used, and finally we achieved with the combination of the MOS2 and the R0 combination nearly 234 millimoles of hydrogen generating it can be possible. So with the extension of this work, now what we are doing, these kind of the hydrogen related panels we are creating. So maybe you may see the solar panels. That means one sunlight and then electricity generation. Why don't we make similar kind of the panels for the hydrogen production? So we are coating these kind of the optimized materials onto the substrates, And then on the terrace of the, even in our laboratory, we made the 400 centimeters square of the big panel for the hydrogen fuel production. So when sun illuminates, it automatically start the hydrogen production from sunrise to sunset. Continuous hydrogen evaluation panels we have already created. So still some of my students, they are working on that one. They are very keenly, we want to extend this kind of work for the large scale, large panels for it. So maybe in the near future, as like you see in the solar panels, similar kind of the panels, it can be possible to produce hydrogen. Once we produce the hydrogen using the different techniques, we can store those kind of the hydrogen and use it for the fuel cell applications. Okay, so for that one we are working. So like we say, we tune the layer number and then we improve the hydrogen evaluation rate. So doping concept and all other techniques also we have used. All these things I think maybe just for understanding point of view. So different types of the materials we use for the hydrogen fuel. As you see here, previously I already explained the metal organic framework. So you see the JDF 67 we prepared. So just a sheet like kind of the morphologies we created. These morphologies we incorporated in the serious materials, and then we are achieving the hydrogen nearly 140 micromoles from once. So, and also you see this kind of the metal organic frameworks, we made the mesoporous materials. That means metal organic frameworks to the semiconductor material, metal organic frameworks to the carbon based materials. All these kind of one single metal organic framework we are using to create a multiple kind of the carbon materials, and single atom catalyst and multiple single atom catalyst also it can be possible to create metal organic frameworks. So all these materials we are using for the hydrogen fuel production. So these are the panels very recently we developed. As you see, this kind of the caskets. So once we place this kind of the panel into the natural sunlight, it's continuously producing the hydrogen. So if you change the different kinds of the material and then keep it in the solar light, continuous evaluation of the hydrogen can be possible. And this kind of the water purification panels also we made. So in the natural sunlight, if you want to get polluted water we are pumping. So in another end, purified water we will get. So the mechanism is the simple thing using the solar energy and the conversion of polluted to the normal water, and also splitting of the water to the hydrogen. So in this panel, what we have noticed is during the catalytic reaction, so say in addition to the hydrogen, oxygen also evolves. So in the same reaction, if you produce the hydrogen as well as the oxygen, it again recombine and then form the H2. That problem we have noticed, and now we are working in terms of the photoelectrochemical techniques. That means in a different chambers, in one chamber hydrogen is evolving, in another chamber oxygen is evolving. So like that chambers we are creating. For that one we need to develop the photoanode materials as well as the cathode materials. So in both cases, either in the case of the anode materials and the cathode materials, similar kind of the problem we are noticing the concept of the recombination. So for that one, we are incorporating new kinds of the materials like cold transporting layers, electron transporting layers. We are incorporating into that one, and then we are trying to generate the hydrogen in an effective manner. So in addition to this solar energy point of view, recently we have working in terms of the electrochemical devices also. By applying the electricity, we want to split the water in the form of the hydrogen and oxygen gases. So electrolyzers, even in the case of the 1 gigawatt, so high-end electrolyzers also we are planning to produce in the case of the hydrogen fuel production. So in these cases also this kind of the BI will work with different LDH materials we have coated and then we are using for the hydrogen fuel application. I hope this research, all those things will be much effective. So just see this kind of the inverse apple kind of the structures also. Previously I already explained. So four kind of the materials how we can create these materials, how it can be useful for the applications. So these are the best example. So we are using the PS material and the ordered self-assembly we are creating, and this kind of the architectures we are creating for the energy storage as well as the energy conversion applications. So like this, many materials we have used, and then we are finally we are trying to create this kind of energy devices. So here the device is the PV system. That means, so using the solar panel, from that one electricity will need to be supplied to the PV system. There it can be produced the hydrogen as well as the oxygen gases in a separate chamber. So from the chamber directly we will collect the hydrogen and then for the real applications. So these kind of the works now we are working. So one is the photocatalytic panels kind of the large scale panels for the hydrogen production. Another thing is the PV systems. That means using the solar panels, from that one electricity we will generate, from that one again hydrogen energy we are creating. So and another difficulty what we have noticed in all the applications point of view, whatever the techniques we are using, suppose I use the electrochemical analysis techniques for the understanding of the charge transportation rate. But whatever the technique I am using, it limits the progress of the material. So simple example. So most of you are aware about the electrochemical impedance analysis. Normally we can do it with respect of the solid and liquid interface. Our material is the solid material. We are using the electrolyte solution. With respect to the solid and liquid interface, we are creating the charge transportation rate. All these properties we are using. In the same case, in terms of the XPS, like this analysis, if you go for the XPS, you cannot determine which kind of the crystal structure it is. XRT possible. Further evidence we can it can be possible from the high resolution EEM analysis. There lattice parameters we can notice. Based on the lattice parameters, d-spacing values, we can analyze the crystal structures also. Even EDS mapping also there. EEM. Even at the low level of the EEM, we can capture how elements are distributed. From the EDS mapping, we can analyze that.
While operating the reactor, impedance
electrochemical workstation impedance analysis. The resolution is 10 to the minus 3 milliseconds. But our electron will be transferred much higher than that. Picoseconds or femtoseconds it is capturing. Maybe if you see in this slide, you can understand millisecond. So after that it will be saturated. So whatever the low charge transportation rate also, it can be shown milliseconds. So that is the problem. Even it is in the transfer in the picosecond, it will display only in the milliseconds. At that time you cannot get this kind of the materials have the higher or the lower charge transportation rate. And another property is the solid and liquid interface. So when it combines to the liquid, the properties may vary. So based on that one, we cannot get the exact properties. So under that, this kind of in situ spectroscopic technique is the most powerful technique for capturing the charge transportation. Small from the FECM analysis, we cannot say exact crystallite size. Morphology can be analyzed. Surface morphology can be analyzed. Crystal structure from the XRD analysis and from the TEM exact size it can be because cell penetration depth is not analyzed. So we cannot visualize complete. Suppose one sphere is there, so it is in the narrow area. So from the cell, we can surface morphology we can analyze, but we cannot analyze average size. It can be possible. It is possible to visualize complete spectrum. Then it can be possible.
Non-metal based, carbon based material replaced in the place of platinum.
Mainly graphite it can be useful, but not that much effective like PT and PD. Maybe in the 3 electrode system also. Quantum dots also, the problem is the solubility. It can be easily soluble at neutral pH and as well as the other pH conditions. So that is the difficulty. Maybe in the near future it can be possible.
If we have any organic polymers,
But whether it is stable at the electrolytes, if this kind of the materials it is stable, we can use it. Another problem is organic polymers or these kind of the materials is much expensive than the PT materials. That is another disadvantage.
So generally rare earth metals were discussed, sir. So including to that scandium and yttrium are also in simultaneously active.
In white LEDs.
Yes. So why only those two from the transition series, sir? Why can't it be from the others?
So different materials have different transition. For our applications point of view, we are choosing those materials.
That's what says. Scandium comes under Peri series.
Okay.
Yttrium also comes under Peri series. So rare earths we have taken which is the 4H series. So why only scandium and yttrium is selectively selected? Do we have any specific properties for that?
I am not sure now because white LEDs long back we did. So just to go through it, I'm not sure.
Dopants also we have taken few of the metals and few of the non-metals, aluminates, vanadiates, borates and silicates. So why only exclusively that, sir? If at all we go with the oxidation states, vanadium has a vastly difference with the oxidation states. Scandium also we have a variation in different oxidation states. Why only exclusively this? Neither they belong to the same family, same series.
White LEDs I am not that much strong. So mostly in the semiconductor point of view, we are working even for the photoresistance applications point of view. So we near to mining. So those kind of so these phosphorus materials is for validation point of view. I am not good researcher in radiation research. Magnetism. So recently medical physics also we started, MSc in medical physics. So few faculty they are working on the bio-related those things. Actually we are tied up with the Cancer Institute, our Cancer Institute Kurnool. It's a Cancer Institute So first 1 year they will study technical and then get the degree from college. MSc in medical physics.
Very impactful and informative. Now I request HOD ma'am, Sundar madam, counsel and Kumar answer and Ramchandra editor to please facilitate the resource person.
We are doing. And then we are analyzing the oxidation state and all other processes. Our real application is with respect to the solid and liquid interface, but whatever the analysis we are using or even for the XRD and all other cases, we are using under the vaccine. That means maybe at the vacuum level our materials property may be different, whereas in the case of the solid liquid interface is different. So what we need to do is we need to understand the realistic conditions. That means whenever we are producing the hydrogen, during itself we need to understand the structural properties. We need to understand the materials properties. In situ spectroscopic techniques. That means within the chamber we need to create the XRD spectra during the experimental process. During the experimental process we need to analyze the temp properties. Then only it can be possible to understand the realistic application of the materials. For that one, recently I collaborated with the software professors. Now we are working, whatever the materials we have developed, we are working for the in situ spectroscopic techniques. So, like within the live point of view, so we are capturing all the properties of the structural and electrical properties. So, for that one, so these are the setup what we have using for the X-ray spectroscopic analysis. Actually, this is the third generation synchrotron facility. So, but unfortunately, in India, we don't have this kind of facility. Generation synchrotron. We have only first generation, so the range is very low. You cannot capture the X-ray analysis with that facility. So that's why we mostly depend on the Japan, Korea, and Germany, USA. These four countries have the well-established synchrotron facility. So in that facility, we are trying to build this kind of the spectroscopic techniques, and we are trying to analyzing the properties in a systematic manner. So one simple example I will give. So here the material what we are using previously when we use the electrochemical techniques, the charge lifetime of the electron is the 10 to the minus 3 milliseconds. When I measure this kind of the X-ray probe technique using the same experimental conditions, the charge transfer rate is the kiloseconds or femtoseconds. Now you can understand what is the problem we are facing. With the available techniques, whatever the techniques we have, based on that one we are judging these materials maybe have a limited lifetime. That's why we are adding this kind of progress and all those things. So there, the problem is not the materials, whatever the technique we are using. With the techniques, we are unable to capture the realistic of the charge carrier transportation rate. So if we have this kind of the in situ X-ray spectroscopy techniques, it can be possible to understand the realistic charge transportation rate. Based on this one, it can be possible to tune the properties of the materials. So maybe it may take time to establish this kind of facilities within India. So that's why we need to be dependent on the research laboratories. But very interesting results we have noticed that even 1 picosecond, that means valency band with another materials, the transfer of the electron will take only 1 picosecond. So that kind of small time interval it is moving from the valency band to the another band of the material. So like that way we need to tune the doping properties and all those things. So overall these are the things what we are doing. So mainly we are focusing on the development of the materials, and now we are trying to understanding the charge transportation rates with respect to the in situ spectroscopic techniques, and then we are trying to developing the photoelectrochemical or electrochemical energy devices from the realistic applications point of view. So these are the so main focus energy devices that sustainable point of view. So these are the overall what we are doing at the thank you so much.